Welcome back to the second half of Day 2 of NASA's Green Aviation Summit here at Ames Research Center in California. Our topic for this afternoon is environmentally friendly airspace operations, and our first speaker is Bhanavar Sridhar, a senior scientist for NASA's Air Transportation Systems. His research interests are in the application of modeling and optimization techniques to aerospace systems. He's made fundamental contributions to automated guidance of aerospace vehicles and the development of passive ranging systems to low-altitude, high-speed helicopter operations. He led the development of the future air traffic management concepts evaluation tool, FACET software. That's the software, the picture we showed you yesterday of the little planes over the U.S. skies. And that received the NASA Software of the Year Award in 2006. He earned a BS from the Indian Institute of Science and an MS and a PhD from the University of Connecticut, all in electrical engineering. Bhanavar, you've got about 15 minutes.
Thank you. You saw this yesterday, the goals and the challenges for the energy and environment operations. So I'm just going to skip this slide and go directly to what those challenges are for the Enroute systems. And also in this panel, we have 5 speakers, and 4 of us will be speaking about how operations can help reduce the impact of aviation on climate. Earlier you heard talks about how it can be done using alternate fuels, redesigning engine and airframe. One of the advantages of doing it in operations is whatever you do here applies both to vehicles which are already flying as well as future vehicles. So the goals for the Enroute and the traffic flow management area is that we want to really take all the advances that are taking place in the climate science and bring that into Enroute and traffic flow management area to reduce the impact of aviation on the climate. And we would like to do that in 2 different ways. One is to see how can you use the operations to reduce the impact of contrails or reduce the formation of contrails through operations, as well as look at the various trade-offs between the different types of emissions. So on the chart, you see some things in blue. This is the setup we have to do the traffic flow management research, which really consists of trying to model the traffic flow management or the airspace operations over the United States, and also try to make it efficiently while trying to increase capacity and meet the demand. So we do that by having flight schedules as well as information about the atmospheric and airspace data. And we do that through one of our software tools, which predicts where the traffic is going to be, what the capacity and the airport and airspace capacity is. And we develop efficient flow management, and we also have the capability to visualize this as well as analyze the aircraft operations in various different ways. So we want to make use of this traffic flow management infrastructure we already have, and to this we want to bring in all the new models and concepts that are being developed recently in climate research. So one of the things, all the things at the bottom are the things we are adding to our traffic flow management research, which is already there, which is to sort of bring in both emission models and metrics. By metrics here, I mean some of the emissions are short-lived, some of them are long-lived. How does one weigh these things differently. That's the metrics part, and there is a lot of research in the climate community to say, how do you measure the global warming of different types of greenhouse gases? And the second thing we have added to that is contrail models. The research on contrails have been going on for a long time, since the days of the stealth vehicle. And here, you're not, here the idea is, how do you fly the aircraft to reduce the formation of contrails? And in terms of optimization algorithms, in traffic flow management, we already do system-level optimization to come up with the most efficient traffic flow for all the aircrafts which are flying in the National Airspace System. But in addition to that, what we are trying to do now is to design the aircraft trajectory at the individual aircraft level so that you are able to tailor that trajectory to, say, somehow to minimize some kind of a composite emission index. So I'm going to show how we try to do that in the framework we have. We heard about contrails earlier today. Contrails are contrails or condensation trails are happen when an aircraft flies through the atmosphere and the temperature and the humidity conditions are right. And so generally, the best models we have says contrails, the kind of contrails that contribute to global warming is the contrails which persist for a long time, and some of them also lead to the formation of the cirrus clouds. So contrails which persist generally have relative humidity with respect to ice greater than 100% as a threshold. And the effect of contrails during the day is good because they prevent the ultraviolet rays from getting into the atmosphere, but their effects during the night is negative. But the people who work in the contrails research say that the net effective is bad. That is, the amount of heat that is trapped overall is positive. So this is how the persistent contrail formation model is done in our research. So basically, you get information about temperature and relative humidity from the weather services, what we call as the rapid update cycle, which not only gives you what the temperature and humidity is currently, but also gives predictions of it for the next 6 hours. So using that model, we compute using the relative humidity contours, we compute the relative humidity with respect to ice. And when this is above a threshold, say 100%, those are the regions you're seeing at the bottom left in that figure. And if aircrafts were to fly through any of these regions, then that is where your contrails occur. So people have looked at different strategies for avoiding contrails, and you can do this either tactical, that is, having either an onboard sensor on the aircraft or having that information about where the regions of contrail formation are likely transferred to the aircraft. And there's a lot of work being done at DLR, instrumenting their aircraft with contrail detecting sensors and trying to avoid them. And the implementation of such a thing here would depend upon the ability of the air traffic service provider to give you different routes. And this is, of course, one of the goals of the next gen, where the user preferred routes would be available. So for doing this strategically or on a planned basis, you need models of predicting contrails. So what is important here is whether you use tactically or whether you use a strategic method of avoiding contrails, you are going to deviate from the most fuel efficient route or the wind optimal route. So the research question for us would be to sort of what's the trade-off between the extra carbon dioxide you are going to generate by staying off the wind optimal route in order to avoid the contrails. And also the other challenge is it's not clear how much contribution contrails have to the global warming effect, and that's still a question which is being considered. And the other thing we also have to think of is the timescales of carbon dioxide are in the periods of decades, while something like the contrails are there only for a few hours. Okay. Here is an example. So what I'm trying to show is what kinds of trade-off one can do in order to decide what is the best thing to do. What you see here in the picture is the purple line, purple wiggles are really the wind vectors at different places. Here is an aircraft. This is the trajectory of an aircraft going from Los Angeles to Newark. And I'm showing what the wind optimal route is. The yellow regions are regions where at that particular time, the temperature and the humidity conditions are right for contrail formation. So you can see in order to avoid the in order to avoid the contrails, you are going to stray from the wind optimal route. You can either avoid the contrails completely, or you can avoid the contrails partially. And depending upon how much avoidance you do, you're going to consume different amounts of fuel, more than, let's say, the baseline is the wind optimal route. So I tried to find out how much this would be. And so what I did was I tried to look at 12 city pairs which have lots of traffic in the United States. And I looked at a flight which departs on the hour, 24 per day, along each of these routes, just to get an idea of what is involved. So here is what you see on the plots. There is a trade-off between contrail reduction and extra fuel consumption. So on the y-axis, you see how much time an average flight from from Kennedy to Los Angeles is going through. That's like about 26 minutes. Now, if I try to optimize my routes in order to, if I try different optimization by putting a penalty on for going through contrails, then I will deviate from the wind optimal route. And that, of course, would reduce the amount of time I'm flying through the contrails. So you can see in the curve there, which says JFK to Los Angeles, 2-dimension, I'm doing optimization only in the horizontal plane. And you can see that I can, by spending more fuel, I can bring it down. So that is if I do the optimization in only 2 dimensions. But if I also try to optimize my cruise altitude, I can bring that down, for example, from 26 minutes to about 3 minutes by spending 2% extra fuel. And similarly, the same thing happens for flights going from Los Angeles to JFK. And again, if I try to optimize both the routes and the cruise altitude, my amount of extra fuel consumption is a lot smaller. And on the second figure, or on the figure on the right, does the same things, but now I am doing this for all the 12 city pairs, and the trend is also similar. So for those flights departing on the hour, for all these city pairs, I could bring down from an average of 140 minutes through the contrails to about 20 by spending about 2% extra fuel. So what I've tried to do is say how we are approaching this problem of building aircraft trajectories which which meets the various constraints of providing capacity, being efficient, but also at the same time taking into account the restrictions or to reduce the amount of environmental impact. So we have developed optimal contrail reduction trajectory concepts, and we have been able to integrate this with our fuel facet and traffic flow management software tools. And what it gives us is a capability to do different types of system level studies, to do various emission trade type of analysis. And with that, I'll stop. Thank you.
Thank you.